Hello, and welcome to the next video in my series on basic statistics. Now, a few things before we get started. Number one, if you're watching this video because you're having problems in a class right now, I want you to stay positive and keep your chin up. If you're watching this, it means you've come pretty far in your schooling up to this point, and you may have just hit a rough patch. And I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you, and so should you. Number two, please feel free to follow me here on YouTube and or on Twitter. That way, when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. That does encourage me to keep making them, since I know people are benefiting from them. On the flip side, if you think there is something I can do better, please leave a constructive comment below, and I will try to incorporate that into future videos. And finally, just keep in mind that these videos are geared towards individuals who are relatively new to stats, so I'll just be going over basic concepts. So all that being said, let's go ahead and get started. Now in this video, we're going to continue our discussion about probability distributions. Now in previous videos, I've talked extensively about discrete probability distributions using coin flips and die rolls and things of that nature. So this is sort of an extension of those discussions on probability distributions. So if you want to learn more about probability distributions in general, please go back and look at those videos, and then you can apply that to this one. Now this video is about what is the difference between a Z distribution and the T distribution. Because I know a lot of students see this in their class, in their stats class, but they never really understand why there are two different distributions or what the distinction is between them. They just sort of use the formulas as they're written and get on with it, but don't really understand what's going on. So in this video, we're not going to be doing actually any calculations or anything like that. We're just going to go over a brief discussion of the fundamental difference between the Z distribution and the T distribution, why they exist, why we even have them, and how at some point they actually become indistinguishable. Okay? So this will be a discussion video, and I call it to Z or to T. That is the question. So let's look at some formulas real quick. We're not going to talk about what they are, but on the left-hand side, you'll notice that all those formulas on the left look the same, and they all have a Z term to the right of the plus and minus sign. Now if you look on the right, that looks very similar. Those formulas look just like the formulas on the left. The only difference is that where there's a Z on the left, there is a T on the right. Otherwise, they're the same thing. So what the formulas on the left are saying is that we're going to use the Z distribution, and what the formulas on the right are saying is that we're going to use the T distribution. Now the question is, why? Why do we have these two different distributions that are used in the exact same type of formulas, but we come out with different answers? So that's what we're going to talk about in the video. So here are some opening examples. These are just sort of examples I came up with off the top of my head that sort of introduce why we have these two different distributions. So here's our first example. We randomly select 5 students, that'll be our sample, from a college freshman class consisting of 10,000 students. So this is a large state university. The freshman class has about 10,000 students in it. And we're going to randomly select 5. So our population of interest is the entire freshman class, all 10,000 students. The 5 students will be our sample that we're going to randomly select from those 10,000. So what we do is we find the mean or the average GPA of those 5 students. Then in our paper or report, we say the average GPA of the entire freshman class is whatever we found our mean GPA to be. of those 5 students. How about example 2? Let's say we randomly select 7 days high temperature in Pittsburgh, Pennsylvania, here in the U.S. during any given year. 7 random days throughout the year. We find the mean temperature of those 7 days. Then we declare the average temperature in Pittsburgh is whatever the mean temperature was of those 7 days. Now, what do these 2 examples have in common? Well, hopefully, this should sort of sit with you in a wrong way. Hopefully, at the gut level, these sound problematic. And that is, in the first example, we are basing the entire freshman class GPA on 5 students. In example 2, we are basing the entire year's average temperature on 7 days. And something should it should be a bit uneasy about doing that, hopefully. And that's because there are certain limits of the data we use in our research or analysis, no matter how simple or how involved that might be. When we do quantitative research or analysis, we are most often interested in a large population, sometimes very large population. And here are some examples. The average GPA of a university freshman class, that was our example 1. The prevalence of depression among those aged 65 or older. Think about how large that population is, at least here in the U.S. We're talking millions of people. The number of round-trip miles driven to work by staff members. Well, if your company is very large, and maybe even a multinational corporation, all this different staff members and employees commuting to and from work, that's a lot of employees. Okay, a very large population. Or the number of customers served at a McDonald's during lunch hour. Well, there are McDonald's restaurants all over the world. And of course, the eating times differ from culture to culture. But even if we say here in the U.S., think about how many different McDonald's stores that is. Think about how many customers that is. That is a huge population. But oftentimes in our research and analysis, that's actually what we're interested in. We are interested in the characteristics of that large population. But due to time and cost, we almost always use sample data to represent the larger population. So there's no way we could give every person age 65 or older a depression inventory or survey. There are millions of people. So we would have to select a sample of those age 65 or older and then conduct our research with that sample. And you can think of how this would apply in this other examples as well. We almost always use sample data to get at our larger population. But here's the thing, and this is why we have the Z and the T distributions. That's because sample data is always at best, an estimate or approximation of the larger population from which it is selected. And that should make common sense. If we select, 50 students from our freshman class, well, those 50 students are just sort of a representative sample of the larger freshman class. But it's always going to be an estimate, an approximation at best. In terms of sample size, and then again, this should be somewhat intuitive. As our sample size becomes small and small and smaller, we are less certain that it is representative of our entire population. There is a greater risk of error. And let's take the logical extreme of this. Let's say I'm interested in the average temperature in Pittsburgh. I pick one day out of the year and say, well, that's representative of the entire year. What if we happen to pick December 28th? Is December 28th representative of the entire year in Pittsburgh? Well, no. Of course it's not. Now, we may get lucky and pick something, a moderate temperature, and it might, by luck, be representative of the entire year. But there are variations in the temperature. It's hot in the summer, it cools off in the fall, it gets very cold in the winter. But if we happen to pick one day that's at the extreme, then that's not a good representation of the entire year. And you can see that as we take more and more days in our sample, we're likely to get days that are all throughout the year. And that should be sort of intuitive to you, at least I hope. Adding to this, we often know nothing about our population. We don't know the population mean, we don't know the population's variance, or of course its standard deviation. Going back to our temperature example, unless we have all the high temperatures in a spreadsheet that we could easily do some calculations on, we don't have this information. We don't have the population mean of all the days. We don't have the population variance. So we're going to have to use our sample to figure those things out. Now, on rare occasion, we do have the population variance or standard or deviation, but most often we do not. So we are strictly relying on our sample to learn more about our population or to estimate different statistics about our population. So what does this come to? Well, it seems like we're kind of flying blind. We're using sample data from a larger population about which we have little to no information. For example, think about your employees if you're interested in their number of miles they commute to and from work. Well, you probably have no way of knowing that. To know that for every employee, you'd have to know exactly where they live. You'd have to find out exactly how many miles they travel back and forth. And that is a tremendous burden to do in terms of collecting data. But if we select a small sample or a decent sample of our employees to figure that out, we can make some estimations about the larger population if our sample is random and representative. So the sample is very important. And that is we're leading to why we have the Z and T distributions. So now this brings us to the size of our sample we're talking about. And hopefully at this point it should be intuitive that the larger our sample size, the more confident we are that it is representative of the entire population. In a larger sample, we are likely to capture all of the natural variation, sort of the natural diversity, the natural ebb and flow of our population data. So again, if we're looking at the average temperature in Pittsburgh, Pennsylvania, if we select one day, we could get August 2nd and it's 95 degrees. Well, we wouldn't say that's representative. But what if we select 30 random days? Maybe we'll get a day or two in January, a day or two in February, maybe 3 days in March. Maybe we get none in April. We get a day in May and so forth. If we have a good sample throughout that year randomly, we're likely to capture all of the high and low points of the temperature variations throughout the year. Same thing with our students. If we have a large enough sample, we're going to capture students that are doing average. We're going to have some students that are doing very well, and we're going to have some students that are struggling a bit. But most students will sort of be in the middle, sort of clumped there in the middle, but only if we take a large enough sample size. A small sample increases the chance that we either miss the natural variation in the data or we overemphasize it. So if we select 3 employees and we're interested in their daily commute, and let's say they live and work in New York, maybe they commute 60 miles to and from work. Well, or in any big city. That's not going to be the same for all the employees' commute distances. So a large sample will sort of even out or capture all the variation. Now there is a point here to make, and that is, as sample size increases, it does adhere to this law of diminishing returns. Well, what does that mean? Well, there is a point when increasing the sample size further offers no more statistical benefits, which is good because it makes research more doable. So we can do more research, we can do more analysis, because, decades and decades of statistical work has shown that there is a point where a larger sample size offers us nothing more. It's not going to capture anything different or anything more. So just keep in mind that the goal is not a bigger and bigger and bigger sample size all the time. There's sort of a sweet spot based on the data you're working with and things of that nature as far as a sample size. And we're going to talk about sample size specifically in other videos. But just keep in mind, the biggest sample size you can get is not always the ideal, because it's a waste of time and money potentially. So let's talk about this t-distribution. Why do we have a t-distribution and a z-distribution? Well, it has to do with sample size. Specifically, it has to do with sample size at the low end. So when our sample size is less than 30, or about 30 or less, and or we do not know the variance and standard deviation of the population, we use the t-distribution instead of the z-distribution. Now the z-distribution is likely what you've already learned. When you learn about the normal curve, its shape, the percentages underneath the curve, and things of that nature, you're looking at the z-distribution. Now the t-distribution is similar, but it has very unique characteristics for when our sample size is under 30 and or we do not know the variance and standard deviation of the population. So they are closely related, but the key thing here is smaller sample size. So what does the t-distribution actually do for us? Well, it allows us to use small samples, which when we're doing research and we're doing analysis, that is very beneficial because it allows us to work more efficiently. We can work more quickly, but still do quality work. Now, the slight trade-off is that we sacrifice some certainty in our calculations. So, if I'm interested in the average GPA of the entire freshman class, and I have a sample of 20 students, that I can do a valid question about that. We can find sort of what's called a confidence interval about where the true average GPA lies. But because we're using a small sample, under 30, we're going to use the t-distribution instead. And what that means is that when I say, give or take, this is what the GPA is, give or take, that give or take, or margin of error, is going to be a little bit wider. We're going to have to give ourselves a little bit more wiggle room when we're using a small sample. So we can use small samples, but we have some trade-off with the level of certainty. Now the cool thing about the t-distribution is that it takes our sample size into account. It's dynamic. So we use this concept called degrees of freedom, which I will say a little bit about at the end. But if our sample size is 20, we use 19 degrees of freedom. And I'm sure you've probably seen that in your work up to this point, and we'll talk about what that means here in a second. But there isn't just one t-distribution. There are many t-distributions. In fact, there is a different t-distribution for every sample size. So it's dynamic, it allows us to use small samples, and it changes depending on our sample size, which is great. So there'll be a t-distribution for a sample size of 15, there'll be a different t-distribution for a sample size of 23, and so forth. And what does this do to the shape of the curve? Well, I'm sure you're familiar with the normal standard curve. But what about the T curve or the T bell shape? Well, they look very similar. But what happens is that in the T distribution, the middle of the curve, and we'll see this on a slide here in a second, gets kind of squished down a bit in the middle, and the ends, or the tails, get pushed up. So the middle gets squishier, squished down, and the tails get kicked up and get fatter. We call them fatter tails. And it gets squishier in the middle, and the tails get fatter as the sample size gets less and less and less, gets smaller and smaller. Now, the one caveat to this, and there is sort of a gray area in here, is that below 30, we're definitely going to be using the T distribution. But as we cross the 30 threshold, the sample size of 30, and definitely by a sample size of 100, what happens is that the T distribution creeps slowly up to where the standard normal Z distribution is, and they become almost indistinguishable. And again, this goes to the fact of why our sample size has an element of diminishing returns in it. Once our sample size becomes sufficiently large, there really is no practical difference between the T distribution and the Z distribution. It's only when the sample size is low, below 30, and or we do not know the variance and standard deviation of the population, which is almost always the case. But my point is, if our sample size is, say, 78, whether we use the Z or the T distribution really has no practical difference. However, at a sample size of 19, there's a very big difference. But as the sample size increases, they converge. So let's take a look at that. So here is a graph of some bell-shaped curves. And I want to draw your attention to the pink curve on this graph. That is our standard normal distribution, or Z distribution, the pink line. Now in the different color lines below that, we have sample sizes, different sample sizes. So in this graph, they use K, but we're going to just assume that that is sample size, or it could be degrees of freedom. There's only one difference between the two. It's okay. But notice as we go to K equals 10, what happens to the graph? Well, it gets pulled down in the middle. Now look at the ends. Well, the orange or yellow color is above the pink on the ends, so it gets pulled down the middle and gets pushed up in the ends. Now look at the K equals 5 line. It's pulled further down. We have a smaller sample size. It gets pulled down further in the middle, and it gets pushed up more on the ends. Now look at K equals 2. Now it's really pulled down in the center and pushed up quite a bit in the tails. So you can see the pattern. As the sample size gets smaller and smaller and smaller, our T distributions get pulled down in the center and pushed up in the tails on the ends. Well, what does that actually mean in real life? What it means is that the probability of having a value further from the true mean, or you can think of it, the probability of having a value in the extremes of the distribution, in the ends, is greater when the sample size is small. Okay? So when our sample size is very small, we have a greater chance of having values that are further away from the true mean. We are less certain. To sort of get that into your mind, it's about certainty. Now, as our sample size increases, the graph gets taller, it gets more pointy in the middle, the tails go down because our larger sample size is more likely or more certain that it is representative of the entire population. So that's why these lines, as the sample size increases, go up, go up, go up, and then eventually, as we'll see on the next slide, the pink, and say like the yellow would actually overlap as the sample size gets higher. So let's look at two more graphs, just so you can see. Now, if you notice on the top of this graph, it says the student's t-distribution. That's the same thing. Okay, the t-distribution and the student's t-distribution is the same thing. It's more formally called the student's t because the statistician that came up with this, discovered or derived the t-distribution, he signed his work as student. So it became known as the student's t-distribution. A little bit of history there. So they're the same thing. Now, let's look at the red curve here. That's degrees of freedom of 20. And you can see it's tall in the middle and shorter on the tails. Now look at the green curve. That's degrees of freedom of 3. That's really pulled down in the middle and pushed up in the tails. As you can see, the green is above the red in the tails. Now look at the blue. That's even pulled down further in the middle and pushed up further in the tails. And again, that's just because our sample size, as it gets smaller, we have less certainty. Now look at this one. This one is really good because it demonstrates an important concept I talked about earlier. So let's start in reverse. Let's start with the red curve, which is the shorter in the middle and higher on the ends. Well, we have degrees of freedom of 1. That's a very small sample. As you can see that it's very low in the middle and the tails are very fat. The tails are high in the end. Now we go up to the blue, to the degrees of freedom of 3. So now it becomes taller in the middle and the tails come down. Now we move to the green. The middle goes up even further. The tails come down even more. So what's happening? Our sample size is getting larger. Now let's look at the degrees of freedom of 30. That is the yellow line. So it's quite tall in the middle. The tails are quite low in the ends. And now here's the interesting thing. Look at the dotted line or the dashed line. That's our normal curve, our z distribution, our standard normal distribution. Now what do you notice about the yellow line and the dashed line? Well, they almost overlap. And this is what I mean by the law of diminishing returns in our sample size. It's also why in almost all your textbooks, you will see that it says if the sample size is below 30, use the t-distribution. If it's above 30, use the z-distribution. Well, the real way to think about that is once the sample gets above 30, you're into 50s and 80s and 100s, you could use the z or the t-distribution. Well, why? That's because at that point they're essentially the same thing. They're really only different when the sample size is below 30 and even lower than that. As the sample size increases, they converge and become basically indistinguishable. So, there is greater uncertainty in the tails due to small sample sizes. Okay, because remember, when the tails are kicked up, that means there's more probability in the tails. If we're more certain, we're going to have more probability in towards the middle, in towards the mean. Okay? As our sample size n increases, the curves become tall and pointy in the middle. And of course, note, as I did on the right-hand side, that the degrees of freedom equals 30, which is the yellow, and the normal curve, the dashed line, almost overlap. They're almost the entire, the same thing. So that's why this magical barrier exists at 30, and you'll hear it over and over again in your classes. So the z and the t are really only, distinguishable or different to a large degree when the sample size is below 30. Above that, they become essentially the same. So let's talk about this degrees of freedom idea. Whew. Degrees of freedom is one of the most difficult things to explain in statistics. Many instructors do not even try. Most of mine never even tried. Because we would all ask, what exactly are degrees of freedom? And we are met with that stare of loathing, like, why did you ask that question? And there's a good reason for that. It's actually mathematically, it's complicated. So I'm not going to give you any mathematical proof or any mathematical derivation of degrees of freedom. I'm just going to tell you basically why they exist. So here's my basic non-stats PhD explanation. Degrees of freedom is basically an adjustment to our sample size. So you can see in the t-distribution we were using n-1. In other areas of stats, you might even have n-2 degrees of freedom, or even more. Okay, I can't think of many more than 2, but I can definitely think of examples where we use n-2. It's just an adjustment to our sample size. Well, why? Well, it's linked to the idea that we are estimating something about our larger population, often our population variance and standard deviation. When we do not know the population variance and standard deviation, we have to use our sample variance and standard deviation. So the degrees of freedom is a way of adjusting for that estimation. And again, that's the very layman's way of saying it, but that's basically why we have degrees of freedom. And what it does in practice is it gives us a slightly larger margin of error or wiggle room in our estimates. So if we have a sample size of 20, but we use the t-distribution, that is 20 minus 1, we're going to use the t-distribution for 19, which again will have a slightly lower center and slightly fatter tails. So degrees of freedom is just an adjustment to our sample size that's linked to the idea that we're doing some estimating, and it gives us slightly more wiggle room in our estimates. And again, that's a very, very non-stats PhD explanation. But really, other than that, just roll with it. Just keep in mind it's a statistical adjustment that you incorporate into your work, and don't worry about it. But that's basically what it is. Okay, now 2 more charts and then we're done. There's sort of a decision tree that you'll see in almost every stats book, and actually all the stats book I have has something that looks like this. And it's basically, do we use the Z or T distribution? Now, there are 2 ways of looking at this, and actually in the end they sort of converge. So here's the first question we ask. Can the population standard deviation be assumed known? Do we know the population standard deviation? Yes or no? Well, yes, if we do, we use the Z distribution. So that's our population standard deviation known. Now, if we do not know it, we go down the right-hand decision tree. In that case, we use the sample standard deviation to estimate the population standard deviation. And then once we do that, we're doing an estimation internally, and therefore we use the T distribution. Now, most often in stats, we're going to be using the right-hand side, because most often we do not know the entire population's standard deviation. Because to be quite honest with you, think about it. If we had all the data to calculate the population standard deviation, that means we would have all the data to calculate the population's mean. But we're trying to find the population mean because we don't have it. So that's why we don't often go down the left side. So this one has to do with whether or not we know that population standard deviation or not. Now there's another way of thinking about it. Is our sample size greater than or equal to 30? Well, if it is, we go down the left-hand side if we have a larger sample size. We could use the Z or the T distribution. Well, why is that? Because remember, in our previous graphs we had, as our sample size gets above 30, the T and the Z distribution converge. They become essentially the same thing. And actually in a chart in your book, if you look at the T distribution, like in the back cover or the front cover of your book, you will see that after it goes down to 99 degrees of freedom, which would be a sample size of 100, it just has an infinity sign, and basically means, okay, now you're using the z-distribution. So they converge. That's why if the sample size is large, in a way it really doesn't matter. Now usually in my work, I would go ahead and use the t-distribution because it's a little bit more conservative. So it just depends on what your instructor says to do and things of that nature. Now if the sample is below 30, we definitely go ahead and use the t-distribution because that's what it's for. It lets us use smaller sample sizes with a trade-off in terms of our certainty. So you can use either one of those decision charts. Some classes are going to teach you, one decision path. Some classes will teach you another. Some will teach you a combination of both. But either one's okay. So just review, and then we're done. The t-distribution allows you to use small samples below 30, but we do sacrifice some certainty in our calculations as sort of a trade-off. It's dynamic. It takes our sample size into account. So there are many t-distributions, not just one. Now relative to the z-distribution, the t-distribution is more squished down in the middle and fatter or ticked up on the ends. And that gets squishier and fatter on the tails as the sample size gets smaller. Now, just a reminder, as the sample size crosses over the 30 threshold, and definitely by 100, the t-distribution and the standard normal z-distribution become indistinguishable. They converge. So the t-distribution is most useful at sample sizes below 30. Okay, well that wraps up our discussion on to z or t. That is the question. And I just wanted you to understand the difference of why we have a z-distribution and a t-distribution, where each is used, how they relate to each other, and how they sort of come into play when you're looking at data. Just a few reminders. If you are struggling in a class, I want you to stay positive, keep your chin up. I know that you are smart and talented and you can get through it. So again, have faith in yourself because I have faith in you. Number 2, just remember to follow me here on YouTube and or on Twitter. That way when I upload a video, you know about it. And if you like this video, please give it a thumbs up because it does encourage me to keep making them. On the flip side, if there's something I can do better, just leave a constructive comment and I will try to incorporate that into future videos. And finally, I do want to wish you the best of luck in your studies. If you're committed to learning, then that's what's really important. So, thank you very much for watching, and I look forward to seeing you again next time.